Hello friends, so we have been considering the formation of a stable cavity, growth of it and its transformation into cracks, ultimately leading to the failure of the material. We defined the nucleation of the stable cavity as the transformation from a critical cavity to a supercritical one. So you have a minuscule amount of growth that transforms a critical cavity to a supercritical one, and this supercritical cavity or the stable cavity, it continues to grow, thereby ultimately leading to the failure of the material through the formation of cracks. In the previous lecture, we saw three different modes for the growth of the cavities. So when we talk about cavities in the context of the growth, so this is 3, pardon me. So when we talk about cavities in the context of the growth, we mean the supercritical or stable cavities. So the modes of this growth were the accumulation of vacancies. We saw a grind boundary sliding assisted growth, and we also saw a constraint growth. So as the name suggests, the first mode is governed by the accumulation of cavities, or rather vacancies. You have vacancies propagating towards the cavities, it's being absorbed by the cavity and ultimately the cavities grow. So this marks the first mode of the growth of cavity, and this growth of cavities ultimately lead to the formation of cracks. Now the grind boundary sliding, as the name indicates, once you have the formation of stable cavity and subsequently when you have the grind boundary sliding occurring in the grind boundary wherein you have the formation of cavities, you have elongation in the size of the cavity, and this lead to the transformation of this cavity into a crack. Now the constraint growth is rather bit tricky. What happens in the constraint growth is you have a reduced amount of influence of the stress that is acting on the formation or the growth of the cavity. So if you could recollect, it is the stress that contributes to the formation of or introduction of a gradient in the chemical potential of vacancies. So the greater the stress or that is acting in the cavity or acting on the cavity, the greater will be the gradient in the chemical potential that is introduced, which ultimately leads to the migration of vacancies to the cavities. So when this stress that governs the driving force for the migration of vacancies towards the cavity, when it reduces, you have constraint growth. This constraint growth is because you have your cavities not growing along the grind boundaries alone, but they are impinging towards impinging on the actual material, actual grains. So when you have such elongation or such growth along or within the material, you have a reduced influence of the stress on the driving force. So this is what we refer to as the load shedding. So these are the different modes of the transformation of a cavity into a crack. You have, so when we consider that the overall time taken for the failure of the material depends on the nucleation rate of the cavities and the growth rate of the cavities. So these are the two factors that govern the overall failure of the material. So we are talking in the context of the overall failure of the material. Now the growth, or to begin with, the nucleation, we considered it as an instantaneous growth, a transformation of a stable or rather a critical to a stable cavity. We have seen different modes that are operating the growth. Now all these have been confined to one particular mode of failure, that is through the formation of cavities. So all that we have been considering, both the nucleation rate and also the growth rate. So these failure or these modes or this characteristic features of the nucleation rate and the growth rate are all been confined to a particular mode of the failure, that is the formation of intergranular cavity. So there is another mode of the failure of the material at high temperature. So we have two different modes in which a material would fail. Of course, these two different modes, they all operate in or operate within the framework of intergranular failure. However, this intergranular failure can be achieved in two different modes. One is the formation of stable cavities. We saw the nucleation rate for the formation of the stable cavity. We also saw the growth of the stable cavities, different mechanism by which these stable cavities can grow, and what are the factors governing this growth of the stable cavities. We have seen that. Now, there is also another way this intergranular cracking or the intergranular failure of the material at high temperature can be achieved. So this we have introduced already. So this is the formation of triple junction wedges. So in addition to the cavities, the triple junction wedges also leads to the ultimate failure of the material in an intergranular fashion. Now, as the name indicates, this is formed exclusively at the triple junctions, and this assumes the shape of the wedge. Now, a more technical name for these triple junction wedges is wedge-like microcracks. Wedge-like microcracks. So, there are two modes in which intergranular failure is achieved in a material, is established in a material at high temperature. One is through the formation of stable cavities. So again, since we are talking about the failure of the material, when I say cavities, it implicitly means we are talking about the stable cavities. The other mode in which the intergranular failure is achieved is through the wedge-like microcracks. Now, when you talk about, or when we consider both the nucleation rate and also the growth of the cavities. So when we consider the nucleation rate and the growth rate of the cavities, the factor that largely governed both the nucleation and the growth rate was the migration of the vacancies and the absorption of the vacancies. So both in case of nucleation rate and also in growth rate for the cavity, it's largely depends on the rate at which the vacancy migrates. So this means both the nucleation rate and the growth rate of the cavities depends largely on the grain boundary diffusivity of the vacancies. And if you could recollect, the influence of temperature on creep is largely through the diffusivity, and therefore the temperature largely governs this particular mode of failure. So whenever you have the intergranular failure being achieved by the formation of cavities, both the nucleation and the growth of the cavities, it is hugely dependent on the temperature, and it is reasonable to state that this particular mode of failure, that is the intergranular failure achieved through cavities, it is largely operational at relatively high temperature. So this relatively high temperature observation of the formation of cavities and the subsequent mode of the failure is because the dependence is largely on the migration of vacancies, and this migration of vacancies is governed by the grain boundary diffusivity. Now, at relatively low temperature, what you would observe is the formation of this wedge-like microcracks. So, at high temperature, when you have sufficient diffusivity when you provide sufficient diffusivity for the vacancies to propagate towards the cavities, you have the intergranular failure being established by the formation and the growth of the cavities. When the temperature is not sufficiently high, the intergranular failure is achieved by the formation of wedge-like microcracks. Now, these wedge-like microcracks, as the name indicates, they are formed at the triple junction of the microstructure. This is the spot where these wedge-like microstructures they form. Now, it is important to note the difference between the terminologies that we use. Here, we refer to this triple junction wedges as microcracks, but here we refer to the other precursor for the formation of cracks as the cavities. The reason is because implicitly the size of these precursors are different. When compared to the cavities, when the microcracks are formed, they are a different size. They are considerably larger when compared to the cavities. So therefore, we refer to them as the microcracks. So when you have a relatively low temperature, the intergranular failure is usually established by the formation of wedge-like microcracks at the triple junction. At high temperature, you have the formation of cavities. Now, let us consider what is the mode that is governing the formation of this triple junction wedges. Now, as the name indicates, we have seen that it forms at the triple junction, and it operates at relatively low temperature. Again, it is relatively low temperature. Now, the phenomena that governs the formation of the triple junction wedges is none other than the grain boundary sliding. So there are different ways the grain boundary sliding facilitates the formation of the triple junction wedges or the wedge-like microcracks. So let us see few of the ways how the triple junction leads to the formation, or rather how the grain boundary sliding leads to the formation of these triple junction wedges. Supposing you have a setup like this, and you have a one grain boundary that is sliding, and the other two remains still. So in this case, the wedges that is being formed will be of this form. Rather, will be of this form. So what we essentially have is, in a triple junction, you have one of the grain boundary that is sliding, and correspondingly the shape of the wedges that is formed varies. So you have a wedges of this shape. So the wedge-like microstructure will be of this shape. Supposing you have the same triple junction and two grain boundaries are sliding. So in this case, you would have a different shape for the wedge-like microcracks. It would be of this form. So initially you had one grain boundary that is sliding, and correspondingly the shape of the wedge-like microcracks vary. Now here you have two grain boundary that is sliding, and correspondingly your shape varies. Now, in addition to the number of grain boundary that is sliding at a triple junction, the orientation also renders a different shape to the microcrack. Supposing the triple junction is oriented in this manner, and here you have two different grain boundaries that are sliding. Now in this case, the wedge will be of this form. So this would be the shape of the wedge in this case. So what we have essentially done is we have changed the orientation, and now you have the same number of grain boundaries at the triple junction that are sliding. You have two grain boundaries that are sliding, and correspondingly the shape of the wedge that is formed and that acts as the precursor of the crack varies. Now there might be also different ways, or rather complex ways, in which the cracks are being introduced at the triple junction. So these can be of this form, wherein you have two triple junctions that are separated by a very small grain boundary. So in the case like this, you have a very small grain boundary that separates two triple junctions. Now in this case, when you have a grain boundary sliding occurring in almost all grain boundaries except for the one that joins the two triple junctions, when you have a condition like this, what essentially happens is the crack forms all along the grain boundary that connects the two different triple junctions. So instead of being confined to one triple junction, in a convoluted case like this, wherein you have a small grain boundary separating two triple junctions, because of the proximities of these triple junctions, you have a crack that is being introduced, rather an intergranular crack that is being introduced in the grain boundary that is separating these two triple junctions. And finally, another convoluted way in which the wedges can be formed is a condition like this, wherein instead of having a similar setup, wherein you have two triple junctions being separated by a very small grain boundary, and instead of grain boundary sliding occurring in all the grain boundaries except for the grain boundary that connects the two triple junction, if a scenario is introduced wherein the exact opposite of this happens, wherein the grain boundary sliding is observed only here, but not in any other grain boundaries, then in that case, correspondingly, the shape of the wedges would vary. The shape of the wedges would be of this form. So depending on the grain boundary sliding, so the first principle is the growth or the introduction of the wedge-like microcracks at the triple junction is principally through the grain boundary sliding, and depending on how the grain boundary sliding occurs at the triple junction, the shape of the wedges vary. Now there will be some convoluted cases wherein two triple junctions are joined by a small grain boundary. So in those cases, it is possible that the microcracks are along the grain boundary, not just confined to the triple junction, but all along the grain boundary that separates two triple junction. And additionally, when you have a reduced grain boundary sliding in similar setup, like in 4 and 5, when you have a reduced grain boundary sliding, meaning the grain boundary sliding is confined to the grain boundary that connects the two triple junction, and correspondingly the shape of the wedges that are being introduced also vary. Now these are the different ways, or these are the ways in which how the grain boundary sliding, or the dominance or the feature of the grain boundary sliding, or the number of grain boundaries this sliding occurs, influences the shape of the wedges that are being formed. Now, in addition to these influence of the grain boundary sliding on the formation of wedges, it is important to note that the propagation of these wedges, or this propagation of these microcracks, is much different from that of the cavities that we saw in the previous lectures. So in case of cavities, when cavities is operational, when your intergranular fracture is being established by cavities, what you essentially have is formation of numerous cavities along the grain boundaries, and that is the reason why we have the nucleation rate, or an expression for the nucleation rate. So this means you would have the formation of numerous amount of cavities, and these cavities are randomly, or these nucleation is heterogeneous in nature. The reason for it we saw in the previous lecture, and therefore you would have a setup like this. So if you have a polycrystalline microstructure, something like this, the cavities will be forming along the different grain boundaries. The stable cavities, they will form along the different grain boundaries. They nucleate heterogeneously depending on the various conditions that we have considered, and depending on the free energy change particularly. So once you have such a condition wherein you have several cavities that have been already nucleated, when these cavities grow, they tend to interact with each other and thereby establishing an intergranular failure. It is not just one cavity that is operating, but you have several cavities that are simultaneously operating. They simultaneously nucleate, they simultaneously grow, they interact with each other, and ultimately establish an intergranular failure. So this is how the cavities, they translate to crack and ultimately establish intergranular failure. However, in case of wedges, it is a two-step phenomenon. In case of wedges, or when you have a wedge-like microcracks operating or governing the failure of the material, in those cases, you have a two-step phenomena, meaning you would have the formation of stable microcracks. So in case of the microcracks, you don't have to distinguish between subcritical, critical and supercritical microcracks, because as the name indicates, the cracks are formed that are they are much much larger than that of cavities, and they are usually stable in nature. So whatever cracks that are being formed, they are stable microcracks, and these microcracks, there's two steps that are involved in the translation of these microcracks into the intergranular failure is the growth of these cracks and the subsequent formation of other cracks. So again, when we say cracks, it's microcracks. So what I mean by that is, so once you have the formation of cracks because of the grain boundary sliding, meaning microcracks because of the grain boundary sliding, these cracks begins to grow. and once they hit a triple junction, a new crack needs to be introduced before they propagate across the triple junction. So when you have a microcracks that is growing and it hits a triple junction, so this is a microcrack which is being characterized by, say, in red rather. So this microcracks, it hits a triple junction. So these two are the grain boundaries. Now you need to have the formation of another microcrack to introduce some sort of a discontinuity, some sort of to separate or to bring about a microcrack in this grain boundary. So you need to have a separate nucleation occurring in this, or separate formation of the microcracks in these two grain boundaries. So these triple junction acts as a point or as an impeding point for the propagation of the wedge-like cracks or wedge-like microcracks. So therefore you have two separate events. Once you have the formation of a stable microcrack because of the grain boundary sliding, then these microcracks grow along the grain boundary and they hit a triple junction, and this triple junction acts as an impeding point. And for the microcracks to propagate further along the other grain boundaries, you need to have a separate nucleating event or a formation event. So therefore, when compared to the formation of cavities, the mechanism for the propagation of the wedge-like microcracks is considerably different. So we have seen the different ways or the difference between the formation of the cavities and the formation of the microcracks or the wedge-like microcracks along the triple junction. And in addition to the formation, there is a difference between the growth of these microcracks. In case of cavities, you have numerous cavities that are formed along the grain boundaries, and these cavities, they grow because they are again operational at high temperature. They grow and they interact with each other, ultimately leading to the intergranular failure. However, in case of the wedge-like microcracks, what you essentially have is formation of this wedge-like microcracks, and once they begin to grow, and once they hit a triple junction, their propagation is being impeded, and for the formation or the propagation of these microcracks and away from these triple junction needs a new event, a formation of the microcracks along the other grain boundaries. So these are like the different ways one can differentiate the cavity introduced intergranular failure from that of the wedge-like microcracks introduced intergranular failure. Now, similar to that of the cavities, wherein we consider the formation of stable cavities, we can also consider the energy change that is required to lead to the formation of the wedge-like microcracks. Now, in that case, in the case of cavities, we wanted to consider the energy condition that favors the formation of stable cavities. So here we want to consider the energy condition that allows for the formation of cracks. So that is a significant difference, meaning when you consider the formation of cavity, it is possible for the unstable cavities to form, and these cavities ultimately they shrink and collapse and completely disappear. However, in case of microcracks, you are attempting to define a condition wherein we are just considering the formation of the microcracks. So once you have the formation of microcracks, what you essentially have is a stable microcracks, and that can grow. So let us consider the energy or the energy condition that will be favorable for the formation of the microcracks. Now, given that the cavities are, or rather the microcracks are considerably different from that of the cavities. One is their size is considerably different, and secondly, when you consider the microcracks of this form, like that is here, you have the microcracks that has considerable interaction with the surroundings. So when you consider a microcracks, you can distinguish two aspects of the microcracks, or you can distinguish the region wherein the microcracks are growing into two. One is the microcrack, other is the surrounding grains. So supposing you have a microcrack that is growing like this, you can distinguish this region, this whole of this region into two. One is the grains here, so you have grain 1 and grain 2. Other region is the microcracks. Now, the reason we can distinguish this into two regions, that is the actual grain and the microcracks, because like we have said, the microcrack is of sufficient or significant size. So therefore, unlike cavity, you can distinguish the microcracks as a separate region that is comparable to that of the grains. Now, the reason we need to consider or the size of the microcrack is because when you consider a constraint growth of the cavity, the factor constraint comes only when the cavities impinge on the actual grain. As long as the cavities are growing along this grain boundary, you don't have any constraint growth. But once your cavity begins to impinge on the actual grain, the stable grains, or rather the perfect grains, so to speak, once you have this interaction between the cavities with the grains, then you have to talk about the constraint factor. So the reason constraint factor or the constraint is brought about is because of the interaction between the cavity and the grains, and this constraint growth occurs when you have the cavity of a sufficient size. Only when the cavity is of a sufficient size and a sufficient shape, you have this particular interaction. When the cavities are small, you rarely have this constraint growth. However, in case of microcracks or the wedge-like microcrack, you already have an increase in dimension or the size of this precursor. So that means you already have the interaction of this precursor with the perfect, or so to speak, the perfect grains. So therefore, your energy consideration will considerably vary when you compare the energy consideration that you made for that of the cavities, the formation of the stable cavities. So let us now consider that particular energy consideration with respect to the interaction of these microcracks with the perfect grains, so to speak. So the change in the overall energy density that is brought about by the formation of the microcracks is the combination of change in the overall energy density that is brought with the surroundings and that is brought within the wedge-like microcracks. So you have the energy density change that is largely confined to the wedge-like microcracks and the energy density change that is brought about by the surroundings, that is the interaction between the wedge-like microcracks and the surrounding. Now let us begin by considering some aspect that we already know, that is the energy change that is largely associated with the wedges. Now when you have the formation of wedges similar to the cavities, the formation of the wedges involves the formation of new surfaces. So the wedge formation is accompanied by the formation of new surfaces. So that means the energy of the system due to the formation of these new surfaces is increased. However, when these surfaces are formed, since they are largely forming along the grain boundaries as well, so if you consider here, irrespective of the shape of the wedges, which depends on again the grain boundary sliding or the amount of grain boundary sliding that is experienced around the triple junction, a considerable amount of grain boundary is being consumed. So irrespective of the shape of the wedges, you have a considerable amount of grain boundary that is being replaced. So here the whole of the grain boundary is being replaced. So that means in addition to the formation of the new surface, which increases the overall energy density, you have a considerable replacement of grain boundary. So you have two counteracting factors. One is the formation of the surfaces, the other is the formation or the replacement of the existing grain boundary. So these two, they depend largely on the dimension of the microcracks. So these two, they largely depend on the dimension of the microcracks. Now when you want to quantify the dimension of the microcracks, supposing if rather you consider a triple junction and you have a microcracks of this form, say for example. Now this here, this height here, let us so to speak, so this height here or the size here is referred to as the crack opening displacement. So the height here is referred to as the crack opening displacement, and the overall size of the crack, or this a dimension, the magnitude of the crack along this dimension, the dimension that is mentioned here, is actually referred to as the size of the crack. So you have two dimensions or two parameters that govern the size of the crack. One is the crack opening displacement, that is h, and the a that actually refers to the size of the crack. 2a that is actually refers to the size of the crack, and this is how the size is calculated in this axis or in this direction. The height or the crack opening displacement is calculated in this direction. So h is here and 2a is here. So when I say, or when the change in the overall energy density due to the formation of surface and the replacement of the grain boundaries is governed by the dimension of the microcracks, it means it is governed by these two parameters, that is h and a. And similarly, it is also governed by the energy density of the surface and the energy density of the grain boundary it replaces. So you have the constants, that is the energy density of the grain boundary that the wedge-like microcrack replaces, and this here is this energy density of the surface that has been now newly introduced, and we have the dimension of the cracks. So this is one of the energy density contribution that is largely associated with the wedge-like microcracks that governs the overall energy change. So this is just one of the factors, that is the combination of formation of new surfaces and the replacement of the grain boundary. So the other factor that is associated with the wedge, not with the surroundings but largely associated with the wedge, is the relaxation of the normal stress. So this is similar to that of the cavities. So even in the formation of the wedge-like microcracks, you have the relaxation of stresses. So this relaxation of stresses, it reduces the overall energy density of the system. So you might ask, from where does the stress come from? So this, you should remember that we are talking in the context of the creep testing, and because of this creep testing you are already imposing a mechanical condition, a tensile stress, so to speak, on the material. So your material is experiencing both high temperature and the stress, and once you have the formation of this particular wedge-like microcracks, there is a relaxation of the stress. Now this relaxation of the stress, particularly the normal stress, or this overall energy contribution of this relaxation of the stress, it depends on the magnitude of the normal stress that is being relaxed. Again, it is proportional to the dimension of the cracks. So all these factors govern the amount of energy density that is reduced because of the relaxation of the cracks. So when we are exclusively considering the energy reduction or the change in the overall energy density of the system with respect to the wedge-like microcracks alone, there are two major contributions. One is the introduction of the surface and the replacement of the grain boundaries. So while the introduction of the surface increases the overall, so this term here, while it increases the overall energy density of the system, this term here, let me use blue, red, stop, blue, go. So this term here, that is the replacement of the grain boundary, it reduces the overall energy density of the system. So, and similarly, the relaxation of the stresses, it reduces the overall energy density of the system. Now, when compared to the cavities, because of the size of the micro cracks that are being formed, the role of the stresses is considerably more important in case of the formation of micro cracks. If they repeat, given that the size of the cavities is considerably low when compared to the formation of the microcracks, the role of the stresses is considerably high in the formation of microcracks when compared to that of the cavities, and that is the reason why we have placed this influence of surroundings in here. So whatever influence that we have now considered, whatever change the system experiences that we have now so far considered, is largely confined to that of the wedge-like microcracks that are being introduced. So because depending on the wedge-like microstructure, depending on microcrack, depending on its dimension, you would have the contribution because of the surface that is introduced, the grain boundary that is replaced, and the stress that is being relaxed. Now, because of its size, the microcrack also influences the surroundings. These surroundings mean the stable or the close to perfect grains. So the way these microcracks influence the surroundings is through the stresses. So in case of cavities, because of its size, we don't have to consider the influence of the growth of the cavities on the neighboring grains, but given the size of the microcracks, we have to consider the influence of stress on the neighboring grain. During the formation of these cracks, these microcracks, you have the neighboring grain that are being pushed. So these neighboring grains that are being pushed while these microcracks that are being introduced in the triple junction. This introduces a significant amount of stress accumulation in these regions. So this stress accumulated because of the formation of these cracks, particularly the shape of these cracks that allows for its interaction with the neighboring grains, we have an accumulation of the stress. So this stress, it increases the overall energy of the system. So far we have considered the change in the energy of the system that is introduced by the wedges. So this one and the other two here, they all relate to the change in the energy that is introduced by the wedges. Now if you consider the change in the energy that is introduced by the surroundings, now one factor is the accumulation of the stresses that is brought about by the growth of or the formation of the grind boundary, or rather the triple junction wedges. Because of its shape and because of its size, since a significant amount of the wedges it impinges on the grain, you have the accumulation of the stress along the grain. However, since once the stress or once the microcrack begins to grow, or once you have achieved a balance between the shape of the microcracks and the way these atoms are arranged in the actual grain, there is also some amount of relaxation in this stress. So this particular shape of the microcrack not only introduces the accumulation of stress in the neighboring grains, it also helps, it also relaxes certain amount of these stresses when it assumes a definite position. So when the wedges are formed in the initial state, there is a considerable amount of accumulation of the stress in the grains. Supposing this is your triple junction and you have the wedge formation here. Now once the wedge is introduced, you have a significant amount of stress accumulation in the grains. Again, this is not because of the accumulation, or this is not the relaxation of the stresses, but this is the accumulation of the stresses in the grains. Now this is in the initial stage of the formation. Now when your microcrack assumes a definite shape, when a balance between the shape is achieved, the balance in the shape is achieved, there is a considerable amount of the relaxation of the stress. The shape of this microcrack is governed by the stress that is introduced by the grain. So you have two counteracting factors. You have the grind boundary sliding that introduces this particular microcrack, and you have the stress that dictates its shape. So at the initial state, what you have is rather an unstable shape, and once you have introduced this accumulation of strain in the grain, that counteracts with this shape and leads to the formation of this stable shape. So you need to consider the accumulation of the stress in the initial stages and the interaction between the grind boundary sliding and the accumulation of stress that ultimately leads to the relaxation of stress and the formation of a stable shape of the microcracks. So you have combination of different events. So the formation of the microcracks, it combines two different events. So one, you have the grind boundary sliding that introduces the microcracks along the triple junction. Now once it has been introduced, you have an accumulation of stress. So this introduces and this leads to the accumulation of stress. Now the grind boundary sliding and the accumulated stress, now they begin to interplay with each other, leading to or rendering a stable shape to the microcrack. So at the initial condition, you just have the accumulation of stress. However, when you consider the interplay that leads to the stable shape of the microcrack, you have the relaxation of stress. So this again, this accumulation of stress and the relaxation of stress, this all pertain to the grain, surrounding grain, not the wedges. So therefore, what we have is, you have not only the formation of the microcracks, but the microcracks assumes a stable shape. This is because of the interaction between the grain boundary sliding and the accumulation of stress. So therefore, you don't only have the accumulation of stress, but you also have the relaxation of stress. So therefore, you have two counteracting factors. Now, so you have two counteracting factors that are restricted to, or that largely deals with the grains, the surrounding grains of the wedges. So the accumulation of stress, it increases the overall energy density of the system, but since we have a subsequent interaction that leads to the formation of, or that provides a stable shape to the microcracks, and that is through the relaxation of the accumulated stress, we have a decrease in the overall energy density. Now, when compared to the accumulated stress, the influence of the shape of the wedges is governed, or it influences the shape of the wedges. It influences the relaxation of the stress in the grain. So what essentially happens is, when we talk about the influence or the effect in the surroundings that is being rendered by the formation of the microcracks, is once you have the microcracks that are being formed, you have an accumulation of stress in the grains. In the surrounding grains, you have an accumulation of the stress. Now, this accumulation of the stress, it interacts with the grain boundary sliding to render a stable shape to the microcracks. To render this stable shape, you have some relaxation of the stress. So therefore, the shape, it governs the relaxation of the stress, and the accumulation occurs during the introduction of the microcracks. So accumulation of the stress, it increases the overall energy density. The relaxation of the stress, it decreases the overall energy density. So you have the overall change in the energy density of the system is governed by the change in the energy density exclusively due to the microcracks and exclusively due to the grains that surround the microcracks. In case of the microcracks, you have the regular contribution, that is the stress relaxation, surface area formation, and the amount of grain boundary that is replaced. So these all contributions are similar to that of the cavities. However, because of the size of the microcracks, we have an additional contribution from the surroundings. So the way the surroundings interact with the microcracks, it governs how the energy change is being introduced. Now, once at the very moment when the microcracks is introduced, you have an accumulation of strain in the, or accumulation of stress in the grains. And this accumulation of stress, gradually it gets relaxed when the microcracks assume a stable shape. And this relaxation, it decreases the overall energy density of the system. So the combination of the change in the energy density that is brought about by the microcracks and due to the microcracks into the surroundings, the combination of these two, it governs the formation of the microcracks. So the combination of the change in the energy density that is brought to the surroundings by the formation or by the microcracks, and the change in the energy density that is brought by the wedge-like microcracks alone, or within the wedge-like microcracks. The combination of these two, it governs the criteria for the formation of the microcracks. So influence on the surroundings and the inherent influence on the overall energy density by the microcracks. Combination of these two, it governs the formation, not the stable formation, not the stability of the microcrack, but just the formation of the microcracks as a whole. So this governs the formation of microcracks, not the stable microcracks, but the formation of the microcracks as a whole. Now, let us wind this lecture up by considering the propagation of the microcracks. Now, the microcracks, they propagate in a definite manner, because you have the accumulation of strain when the microcracks impinge with the grain. You have an accumulation of strain. There is a definite manner in which the microcracks grow. Supposing you have the formation of a microcracks in this manner. If at this microcrack, it grows like this, meaning the height that we have considered, that is the crack opening displacement. So you have, say, at T1, you have the formation of a microcrack, and this microcrack, let's highlight it in red, and this microcrack continues to grow. And when this microcrack grows, you have a simultaneous increase in the crack opening displacement. The H2 and H1, along with, when compared to H1, the H2 also increases. So with the growth of the microcracks, you have a simultaneous growth in the crack opening displacement. So what this means is that you are increasing the stress accumulation in the neighboring grains. So as the crack opening displacement grows, it means the amount of impinging that this microcrack does with the neighboring grain also increases, so the amount of stress accumulation also increases. So this is not a stable growth mode for the microcracks. So therefore, there is an alternate mode that is being observed. So this alternate mode, it looks something like this. What happens is that when the microcrack grows, the crack opening displacement, the H here, assumes a definite value. So there is a maximum value that H here assumes, and once this H assumes the definite value, and you have the microcrack in this manner, so you have the growth of the microcrack, and when the microcrack grows, the H assumes a definite value, a maximum value, and once the maximum value is reached, the growth, it looks something like this. The growth of the microcrack looks something like this. So instead of having a growth wherein as the microcracks grow along the grain boundary, the H, that is the crack opening displacement, also grows along with it, you have a mode of growth. This is the actual mode of, you have a mode of growth wherein the crack opening displacement remains constant. This is independent of time. So the crack opening displacement is independent of time, it stays constant, and the growth is only along the grain boundaries. So this is the energetically preferred mode of growth when compared to the growth wherein the crack opening displacement increases with the size of the crack. So as the crack grows, particularly the wedge microcrack grows, the crack opening displacement, when it grows as well, the amount of impinging that the grains experience increases, therefore the accumulation of stress increases. So that mode is not energetically favored. So this mode is not energetically favored. So the energetically favored mode is the one wherein the crack opening displacement is constant. So once you have reached this particular crack opening displacement, then the growth of the cavity will be in this manner, or growth of this microcrack will be in this manner. So with this, we will wind this lecture up. So whatever we have seen in this lecture has largely been confined to the wedge-like microcracks. So far we have considered both cavities and the wedge-like microcracks. We will consider the other aspect of the cracks at high temperature in the subsequent lecture. So goodbye.